Good afternoon and welcome to the CERIAS Security Seminar. Our speaker today is Mark Brooks. He is a principal cybersecurity researcher for the MITRE Corporation. They are a federally funded research and development corporation. And his topic today is leveraging internal network traffic to detect malicious activity. I think he's got many lessons learned, so
Wow,
he's going to share some of those with you today.
Okay. All right. Thanks, everybody. I'm happy to take questions as we go through, so feel free. Just raise your hand and let me know. I'm happy to be as interactive as you guys want. I'm gonna grab a chair, like Randy said, I'm with the MITRE Corporation. So this is some research that we did. It's publicly released, which is the reason I can talk about it. So we did it probably I think we concluded about a year ago. So we've done some follow-on, but I can talk maybe a little bit about that at the end of it. But just to give a sense of when this was done. So the idea of the research is I'll set the problem that we really tried to address first, talk a little bit about what previous work we've done, and then talk about the results we've done. So the real problem we were looking at was if you have an external adversary and we had a threat model that we were really working off of, the notion that you have an attacker that does certain steps within their attack suite. They'll breach your perimeter, they'll do some entrenchment activity, some different reconnaissance activity, and then staging of the data. This was really looking at, the notion of data exfiltration, where they're trying to walk out the door with data that you'd rather them not do. And can you detect that, and in what stages can you detect that? So they have some C2, which is their command and control channels, and exfiltration. So the parts in red, really the entrenched, recon, and stage, are activities internal to your network, and that's what we're trying to work on detecting, because there's been a lot of work on perimeter-based detection of activity. So we're trying to find ways to exploit the fact that you can have sensors internally and monitor your internals a lot easier than you can when you're going external to your network. So our big hypothesis of the original research and kind of what we work off as a basic idea is this notion that how internal user interacts with information in your enterprise via SMB, HTTP, other network protocols that you can kind of measure has a specific pattern to it. And then when an adversary compromises that account, they don't know with 100% fidelity how to stay within the parameters of that account. So if they know exactly what a person does with your internal data stores, that's a much harder part of the spectrum, and that's probably going to be beyond detection of what we're looking at. So that's what we mean by this notion of learning curve to masquerade a user, and this detection window, where you have this period of time where if there's a compromise, they're trying to follow their script, do their activity threat pattern without having to really know what the credentials were normally used for. And so that's an opportunity, if you have a model of their previous activity, to potentially see a change in behavior. So given that as a baseline of kind of that's where we're really going from, some background on research that MITRE had previously done was we'd looked at just malicious insiders, the notion that you have a human sitting at the keyboard, trusted user of your systems, and how do you take that as a model to detect when that interaction changes? When is there a bifurcation where you can say, okay, this was malicious activity done by a user versus non-malicious? And that was what that research was really trying to, and we were building off of the detectors and infrastructure of that research with the follow-on research. So this is just a notion of the system diagram from that illicit work that was previously done. It was published, I think, in 2008, but it was done by a gentleman named Greg Stevens at the MITRE Corporation. But the idea of that was to try and solve a triage problem using the Bayesian network to prioritize who's the most potentially malicious user inside your network. So we wanted to extend that. So that's kind of what I'll talk about, is some lessons learned when we extended that work. So go ahead. Yeah.
Is that something that you guys do offline or online? When you try to categorize the threats?
So the categories, when you mean offline, do you mean in real time or okay? Yeah. So the idea is usually the detectors that we were looking at were most based off either volumetric amounts of data or over a time period. So it wasn't real time in the sense that said, okay, this is right now, this minute. It was you build up for the illicit work. He looked at a day of activity. So he built up a day of activity, and the next day, so it would all be kind of ex post. You say yesterday's most potentially malicious behavior was this, and then you kind of had to extend it. So one of the things we realized as we kind of extended this to try and look at APT and other things is the response time of a day is usually inadequate, because once you have a compromise, the change in behavior and the reaction and them going through that whole chain can be faster than a day. So we started to look at how you can build models smaller than that, and I can talk a bit about that. But that's kind of results that we've worked on after these activities. But it's a known issue of how rapidly can you respond and what's the fidelity of your model of behavior. So go ahead. Yeah.
But is that a concern since these are APTs and, they're usually slow to reacting within a day? Is that really, or less, is that really a concern?
I guess I wouldn't completely agree with your notion that they're slow to react, and they're slow. Yeah.
Slow for them to attack. Like they get in and then they spend some time inside the network and then after some time then they will.
Yeah, but the question is, what's your threshold? So there's a spectrum of behavior that an APT would have, and the question is, what is your threshold for allowing that behavior to occur on your network? And that's a kind of a exogenous determination that has to be done of, do you mind them being on your network on the thing, or do you want to have as early warning as possible, and you'll accept the false positives that are kind of, because that's always the tension of, if you start flagging things more quickly, then you're going to necessarily increase your false positive rate. So that it's just a tension that has to be determined based off of sensitivity of the data and other things that kind of outside of what we were looking at. We were just trying to find a model that could we even get efficacy with this. But I think more than a day was usually the response when we talked with folks, because one of the parts of this research was talking with folks running operational security operations centers, was more than a day tended to be too long. They wanted to be able to look at things faster. So if they had something pop, they think there was a spearfish that got through or something like that, they usually want to react to it pretty quickly. So, any other questions? Okay. So the approach we took, this was the approach that we took to try and extend the existing illicit research that had done. We were using our MITRE intranet to develop and test this. So this was our corporate network that was internal to MITRE. And we were modeling the threat, so we hypothesized and enumerated different behaviors that could be done. And then we did the standard thing you do. Once you have behaviors you extract the features that are detectable, you get some sort of signal, and then you're really trying to detect when that signal fundamentally shifts because of, the depiction is when you see the shift because someone's added additional behavior into your mixture. So some preliminary results when we were taking basically the baseline assumption of the illicit work and applying it towards what we consider the APT. So we changed some of the detectors and other things. Was the detectors were really, really noisy, and that was a challenge for us because if the detectors are fundamentally noisy, you are aggregating the signal, so you can work on some of that. But it just became so noisy that we had no confidence that they were really distinguishing between malicious and non-malicious behavior. And that was the thing you want your detectors to do, is to have a relatively low fire rate so you can get a sense that they're not really common behaviors on your network. And the other thing that was the work that Illicit had done was it built up this aggregate like we talked about a second ago, but it was only within a one-day window. So it didn't really extend beyond. It said, okay, today you were the most malicious because of this aggregate of your behavior, but it didn't say we have a trailing window of your past behavior. So it didn't take into account as much as we'd like. And we had some issues with just the nature of the experiments. We were one sensor deployed on a network, so we had a relatively good location to see a lot of activity, but it wasn't 100%. And there's some, go ahead.
Each detector's output is put into the Bayesian or the naive Bayes classifier. Is that how?
So the idea was the detectors were all inputs into it was a naive Bayes. And the idea would be then you use subject matter experts to set up the probabilities to allow you to do classification and triage. And then as you labeled data, you could potentially go back and update the probabilities appropriately.
So what are some examples of these detectors? Is like how many times the user touches a data store?
So some of the examples especially from the illicit work, you'd see notions of is someone printing a large amount of a large volume? Because in known and insider threat cases, one of the ways you exfil data is you just print the data and walk out with it. So that could potentially, are they trying to do really deep searches? In the sense, are they doing a broad search and then clicking through to try and get what they want, but have it be disguised as them just doing a broad search and not know how to search? So certain behaviors that we were known to be potentially furtive, but that search behavior could be just they don't know how to search real well, or they don't know the right term. So that's where you have this notion of you have to have some sort of probabilities involved because there's uncertainty about the activity.
So the detectors are pretty complicated, kind of set up by experts.
Yeah, so what the initial illicit detectors were developed by just case study of what previous malicious insiders had done, and then the APTs extended those to what previous APTs had done, or what we knew, kind of what we were concerned about APTs doing. So, does that make sense? And then the other challenge you have is one of the things that people start to look for is attribution at the network layer becomes a challenge to tie it back to this user account on this host did this activity. Because certain stateless protocols, it's really hard to confirm that yes, it's that person. And then if you add in like things like DHCP, where IPs might change depending on where the machine moved, attribution can be a challenge. So, okay. So that was some of our, so we extended that and that kind of, we didn't really see that as really fruitful. So we started to try and say, okay, well, the detectors implicitly or inherently have this notion of potentially furtive behavior. It's threat-based, this is a threat to someone's activity. So we started to say, can we use anything non-threat-based? Can we extend it or say, let's ignore the threat model or let's put that on the back table and say, what are things that we can use to model behavior or detect when there's a fundamental shift in the behavior? So that opens us up to fundamental shifts occur all the time. Someone gets a new job, someone gets reassigned, other things. So we realize that doesn't give you, you open yourself up to that sort of false positive behavior. But if it's something that's effective, then that's really why we were exploring it. So and that also helps us capture the notion that if they fundamentally shift the behavior but avoid one of the threats that we knew about, so they start doing something weird that's beneficial or what they want to accomplish, but not in a known, what we call TTP, technique for the adversary, we wouldn't be building it. So it's kind of the old trade-off of signature-based versus anomaly-based. So I guess a couple of the things we started looking at is, can we find out who acts like whom and then see when they've commingled activity together. And I'll talk a bit about the models we used. So the first real model we started doing this with was what we referred to as the bag of actions model. If folks are familiar with document classification and categorization, there's a technique called bag of words. And we were really leveraging that as a concept in the notion. So bag of words, for those that aren't familiar, well, is everyone familiar with the bag of words model? Okay, so I see some notes. So just at a quick run, it basically takes a document and ignores all semantic structure of the document and says, I've got a bag, which is effectively what's called a bag of words, and you just put all the words in it and you count them. So you say, okay, I've got, and you might toss out words like prepositions and other things that don't give a lot of context or meaning, but it gives you some sense of what the document's about. So the idea of bag of actions is we said, okay, we're going to throw out a lot about what we know about the activity. We're going to say within this time window, we saw you go to this IP via this protocol or something. So that builds us just a feature space about a person's activity that doesn't tell us a lot, but it gives us some high-level notion of the kind of activities patterns that user did within that time window. And so that's really what we were working with is, say it's independent of potential threat activity. We're just trying to capture a model that says this is the type of activity that a user did. And this was what, like it says here, we implemented that to work with IP addresses visited. So if you imagine a vector for a user at a given time, you have a vector that has IP 1.1, some range of IPs, and you have that person visiting that IP, so they get 1, or some count of the times they visited that IP. And so that just gives you a notion of what the kind of dictionary of activities would be across your user space. So we wanted to use clustering within, so that you could use that to then define a space to do clustering in. You could say who had activities that were similar to another user. That was really the basic crux of it, because we wanted to build. So the idea was we wanted to say, can we cluster users together that are stable enough so when we see someone move out of a cluster, it can raise a flag. We can say you're suddenly acting differently or different than your cohort than we would have expected, and that would cause a flag. So there's a couple things you have to test to be able to do that, and that's what we started testing was, 1, can we create those clusters? And then 2, as we look at them over time, are there measures of stability that we can use to say, yeah, they're stable enough that when someone moves, it's actually something that's worth looking into. Because if they're really unstable from time slice to time slice, then it's not going to be a good signal because you're going to get a majority of false positives or everybody's, just the behavior is just too different. So, okay? Does that make sense? All right. And I guess the one thing at the bottom, and this is clear throughout, that I think a lot of people will need to pay attention to as you do detection work is, you can't imply that it's malicious based off these types of behaviors because it's just a change in behavior. So you don't know anything about maliciousness until you have further analysis. So that was one of the things that this kind of, when it moves away from known threatful activity or potentially threatful activity, the uncertainty of it being malicious does increase. So there's a technique, a paper that we saw from 2010, I can get the reference if anyone's really interested, was the notion of how you measure cluster stability over time. And this is just some simple sample data, but the idea is this is 3 set dates, this is just an illustration, but the nodes themselves in this bipartite graph represent a cluster at a specific time, and then the edges between them and the weights represent the probability that someone from one cluster is in the same membership in the next cluster. So if you look at the graph that I'm looking at, from 1901, I guess the top one, you have some just arbitrary labeled cluster 1. As you look across, you see that it has two edges leaving at 0.5 and 0.5. So that would say that half the membership from one at the first time slice went to the arbitrarily named cluster 1 in the next time slice, and half went to number 2, and then half of 2 went to number 2, and then potentially the other half maybe didn't have activity. So you don't have guaranteed activity at every time slice. So some users will just go away. So potentially membership will drop just because of that, or some people just might be far enough they don't end up in a cluster or something like that. So, and the other thing is we did threshold this to say if the probabilities were below a certain amount, we cut that out. So as we did this over a period of time, the first test was initially say, okay, if we do this, is it stable enough to actually pursue it as a detection mechanism? And this is something that allows, and it has this notion that you have this idea that people visit the same IPs probably pretty regularly over a given time. And we mapped them to, if they were to the same, if the IPs were mapped to the same host name, we did bring them together. I mean, there are certain things where you have to kind of, not every IP is really a unique network resource. If someone's going to kind of your main page and it's just behind a different, it's load sharing across a bunch of IPs, you want to push those all together. And the challenge we had was the stability results were just abysmally low. So as we looked into this, the results were just nowhere near high enough for us to say, okay, if someone moves from a cluster to another, it would be reasonable to assume there might be some APT driving that action or some other fundamental behavior change. It was just people moved from clusters to clusters a lot more than we expected. So that was the challenge. And there's, the best results we saw were about 42% stable over time. And that's still way too low for us to be able to do any sort of detection off of that, because, that's 58% of your population on a given day needing to have evaluation. One of the things, I guess, in our research that we tend to have be the normalization at the end, the normalizer at the end is this something that if I go to an operational guy and say, hey, let's try this out on real data with a real live SOC, is it something they even have the resources to do? And when you start having to check 50 or that much of your population in a given day, it's a non-starter as a potential mechanism. So, this is just really unstable, and we just found it not to be suitable. Now, the one thing is that was, again, an instance of our network at that time. It could change. A different network might have a lot more stability. I mean, MITRE as a corporation has a lot of kind of varied workers that do a lot of different projects on a given day. And so that might be, to some extent, it might extend outside of just the security research to say some instances, some organizations, this technique might work really well if people do the same thing over and over every day. That didn't work in our environment. So. And the other thing is if we timed the activities, there are some techniques that you could do to tweak it, but the stability was so low that and the next technique we started looking at seemed to be a bit more effective. So we started looking into that. So I'm about halfway through on my slides. So if you guys have questions, feel free, because otherwise, we'll go early. But so the next thing we started looking at when we found these clusters being really unstable and we weren't able to easily use that as a detection mechanism, we started looking at what we refer to as protocol graph monitoring. And there was a PhD thesis from Carnegie Mellon that we found about protocol graphs that we're using across the entire enterprise to try and detect when they had different bad things happening in their network. We started saying, okay, well, and the basic idea is, instead of looking across a cohort in a given time slice, can we take an individual's behavior and look at the history of that behavior over time slices and build up a model that when that behavior itself changes, we say, okay, that user has fundamentally changed in what they were doing. So that was the real kind of key insight or driver of this protocol graph monitoring. And what it is it implements it says a graph theoretic model of machine activity. It says, a node represents IP and port, which effectively says IP and protocol. So if you connect from one IP and to another IP with a given port, you'll have a connection in that protocol graph. That's why we call it the protocol graph. And then the weight of the edge is used, that is the number of connections we saw. So that builds out effectively a forest based across the number of protocols you're capturing for a given user on a given day of nodes and the edges. And then the idea is we see unexpected increases, if we build up a model that says this is kind of what we have some metrics about those graphs, and I'll talk about those in a second. If we see unexpected changes to those metrics, and we limit our look for changes to be increases based off of the notion that if a bad guy had compromised an account, he's just adding to your behavior because you're going to still be doing it. With the notion that if he stops you from behavior, if he mitigates your ability to do what you need to do, there are already other mechanisms to detect that. You call the help desk and say, I can't do what I need. You call when you can't do what you're normally doing on you'll usually reach out to someone in your enterprise and say something's wrong. And that would trigger another, that would affect being alert about an APT. So we just said, well, what if he increases your behavior? So you might not notice that suddenly your username is going to a bunch more SMB shares than you had been in the past. So that's really why we use the idea of increases solely, not just increases and decreases. So here's just a sample graph to kind of walk through what I was just talking about. If you look at the, I guess it would be your right side of the screen, is that right? Yeah. There's a graph that's labeled A1, then B1. So that A1 to B1 would be the notion of the protocol 1, and whatever that is, it's just an arbitrary number for that. And then you see there's 5 nodes in that graph for that protocol, and then the other protocol has 2. And one thing you could infer from that is the user account must have logged in at A for protocol 4 and maybe from F as well, because it's not a completely connected graph for that protocol. So we built it. What we did was we built these as we ingest the data, and this is where we started moving past just the one day. The initial research was just a 1 day of activity. You build up this activity model, this protocol graph for every user for a day, and then you compute some metrics. So then as you build that model, the metrics really are the characteristics that you're grabbing instead of the actual graph there. You don't have to keep the graphs in memory. So it ends up being relatively lightweight to keep all of everyone's model in memory. So the goal is, like I said, can we use this when beyond normal expected activity? Can we use these to detect when they're potentially malicious? So, and again, this has the same constraint that we had when we talked about the BOA clustering, is that if we do see an increase, it might be just they suddenly got a new job and they're really busy, or something that caused a shift in behavior that's not fundamentally bad. So, are there any questions? I've kind of okay. So so what we did when we looked at the work for the protocol graphs, we generated some metrics that basically help us capture some of the behavior of a user within the network. The first one being the graph size. This was, just straight standard graph model. The number of vertices, and then the number of edges, the largest component size, and the number of components, and the number of connections. So some of them are distinctly, like the number of edges is going to clearly have some correlation to the number of nodes. If you increase nodes, you're going to have to implicitly increase edges. And we realized that, so there's some of the signal does have some overlap, but this is kind of what the Collins work had done initially, so we wanted to use that as the baseline, and then potentially if we saw interesting results, the follow-on would be to tweak that. And then the other thing was, as you build out these metrics, so for each of these 5 metrics, you could compute a number for a given protocol graph. And then as you have enough observations, that number then you can compute to say, what the mean number is in your model, and then you can say, is it a Poisson distribution or a standard distribution, and then what would be the standard deviation from that. So the equation at the bottom, where you have the evaluation of x, you look at the the mean for x, and then you look at some basically the t is the knob you turn on how many standard deviations above or below, above in this case, above what we would have expected is going to flag something as anomalous. So eval x would either come back as 0 or 1. 1 if you say, okay, for this metric, for this observation, we consider this anomalous. And then the configurable part of that would be how many thresholds above standard deviation, how many thresholds above the mean how many standard deviations above the mean would have caused that to flag. Go ahead.
As you aggregate samples for your model, do all the samples belong to a particular class, or is that something that you're going to determine with this model?
I'm not sure. I'm not trying to understand your question.
Mentioning that to compute the mean, you keep adding samples, right? Like you measured
So
all these 5.
walk through an example. If I'm computing the mean, if I go back to this graph here for the sample graph, if I'm trying to compute the mean of say just the number of nodes, if you say you would count the number of nodes in a given day in a given protocol, and that would be the measure for that day. So if you say in SMB you went to 5 different hosts on the network, so we saw 5 different nodes of activity, IP activity on that protocol for you. On the second day we saw 10, right? So then you would have 2 numbers, 5 and 10, and then you build out some observations over the time for a user. So each user has a protocol graph for the time window you're looking at. In this case, we were looking at a day. And so, and then once you have enough observations, you then have the metric enough of a model to figure out what the mean is and the standard deviation
For all the users?
for that user.
Oh, for that
Yeah,
particular?
once you have a number, you have to have observations of a given user, right? So I don't assume that user A and user B have similarity, right? I'm looking at what was user A's history. Is user A looking different than he did? I'm not. So all basically, effectively, all users are compared to themselves, but nobody else. That's just part of the way we were approaching this. We kind of felt like this was a different enough approach than when we looked at users compared to people that did similar activities. It was really kind of all over the place and unstable. So that's kind of why we wanted to try this and see. So, make sense? Okay. So, well, I think I already said this. So this is really kind of the evaluation we did, and then what we did was like I was starting to, if a specific metric for an actor in a given time frame exceeds the mean and thresholded standard deviations above that mean, we label it as anomalous. And again, so just to be clear, I was the one that implemented all of the BOA, the clustering work. This work was done by one of the fellow researchers at MITRE, Carrie McKay. That's her name was on the slides. So just so you guys know, this was her work. But then we labeled it when the observed graph. So effectively, you walk into you have a model with a mean, a standard deviation, and a user set threshold or a kind of, a sensor set threshold that says if it's above this many standard deviations for this metric, label it as anomalous. And the anomalous meant 0 or 1, and that's really what we did. And then what that implies is, given that you have 5 metrics, you get an anomaly score for every user on a given day between 0 and 5. 0 being none of the metrics were above the evaluated to be anomalous, and 5 meaning all of them. And then, of course, that's how you'd get 0, 1, 2, 3, 4, and 5. The way we did the experimentation was we had synthetically generated bad actors, and this is a kind of a sticking point and a challenge whenever you start doing detection research and experimentation, is how do you get bad guy data into your good guy data to find them. You can synthetically generate, and I'll explain how we synthetically generate it, but the other thing you can do is red teaming and other activities, but there's always kind of challenges, and rarely, if ever, and I'll talk about this, is rarely, if ever, do you have good exemplar data of what a bad guy did that you can go back and replay. It's just very rare will anyone share that with you, and if they do, it's a challenge. So when I say 32, 39 known bad, that means what we did was we said, okay, well, we're not talking about threat-based activity, so we just want to be able to detect when user A is suddenly different than what we'd expect user A to be. So we just took a different randomly determined user and laid it on top of A's activity pattern. So we perturbed it, we automatically perturbed it, but the question is, can we detect whether we perturbed it enough to have it flag? So we didn't know what we were laying on top of it, and so the randomness allowed us to get some confidence that the detection is really telling us when the behavior changed, instead of, we didn't try and stack it and say, oh, well, this is a really noisy guy, let's lay him on people, and we just randomly picked users and laid them on top of other users. And that's what we mean by synthetically bad actors. Because we said, okay, that means the guy that had someone activity laid on top of him suddenly is doing a lot more behavior than we would have expected, because the generating function, the actual hands on keyboard or APT or whatever, has now 2 or 3 people instead of just 1. Does that make sense? Is that clear? Okay. So I don't know how many people understand ROC curves, but they're pretty standard in the detection literature and data mining to talk about what the trade-offs of false positives and true positives are. So the receiver operating curves, I believe, I'm not going to explain them in huge detail, but I'll talk about what they are and say. I guess one thing to be clear is, so these ROC curves are pretty good for operational usage. They're not good. You wouldn't publish these in a data mining journal just because they're not that good. So the idea of these is the x-axis is your false positive rate, and the y-axis is your true positive rate. So if you have a perfect detection mechanism, it's going to be in the upper left-hand corner, because it's going to Just making sure I'm not looking at the mirror. But it's going to be basically at 1, 0, right? Or at 0, 1, because you're going to have perfect true positive and 0 false positives. That really never happens. So what you do is over some spectrum of how you tune your detection mechanism, you measure how well your system is on the true positive versus false positive. Are you guys familiar with this? Am I explaining something? I don't want to explain. Okay, if you're all familiar, I don't have to explain it all. But what we were looking at was this notion of if we use 7 observations, meaning we have 7 previous days to build up that mean and determine what the standard deviation is, how does the effect of basically we have 5 lines on the charts, and I don't know if you guys can see this very well. If not, I mean I can make these available if you're interested. But yeah, there are kind of 2 levers that I talked about that you would be of interest. The difference is what's the anomaly cutoff score? Like if you get that score between 0 and 5, when do you label something anomalous? Does it have to have all metrics fire as anomaly, or does it just have to have 1? So that threshold of 0 to 5 is what gave you the different points on the graph. The different lines themselves are how many standard deviations you're using to determine if it was an anomalous or not, if that makes sense. So depending on, so if you say t equals 5, that means it has to be really well above what the expected standard deviation is before you label it as anomalous. If you say t equals 1, it just has to be 1 standard deviation above. And then as you go across, the question, then it's a question of if you say 0, so you're going to label everything as bad, you're going to have 100% true positive, but 100% false positive. So that's the upper right-hand corner. And if you label everything as good, then you're going to have 0% true positive and 0% false positive, because you're not going to label anything incorrectly because you're late. Well, so that's kind of the charts. And this is, so one of the things, and I'll have, so the first one was on the first data set, December 1st of 2009. That was based off the live data capture we had, so that's why we have a specific date in there. And then the second one is the 22nd. So those are 2 different dates that had behavior that we were interested in. Mainly we had a bunch of data, and this was kind of when we generated the synthetically bad users into the data. So that's why. So the area under the curve is usually the measure that kind of gives you a general sense of how well it's doing. So this is the area under the curve measures that we'd gotten for the December 1st experiment and the December 22nd experiment. So this was, and those are kind of, they're not horrendously awful numbers, but they're not great. You'd expect better if you were going to do kind of, if we were coming up with a really new algorithm or something. But this was enough that this was markedly better than the 42% stable we saw for the bag of actions clustering. So that's really, when we got to this point, we said, okay, well, there seems to be some nice things here. There's clearly, it's not perfect, right? We do have false positives, and we need to work on exactly around it. But this is kind of where we ended up getting some results that were of interest to us. If you look, the Poisson distribution assumption, that goes back to how we calculate what the standard deviation is and whether it's a normal or Poisson distribution. The area under the curves are a little bit better from our estimation. So that's kind of what our findings is, that Poisson seems to be a bit better than normal. So this is kind of the results we ended up with. So we have we thought they were promising, not exceptionally, not real significant, but the nice thing is it seems like it's a model that you can tweak and see the results, and that's one of the things that we liked, is that we could, and it's not very expensive to keep these models memory and resident, so you don't have to keep a large graph in memory. You can just keep the mean and the standard deviation, the threshold. All the t's were set to be the same for every metric, so that'd be another area that you could do more experimentation on, is some metrics are more valuable than others. We assumed every metric was equally valuable, so you got a 0 through 5 anomaly score. That's not necessarily true. Some of them, like I said, we know when looking at them, some of the metrics capture the same signal or change in behavior that other metrics do, so you might want to tease them out and make them separate so you get a more distinct signal. Or some of them just might not be valuable, right? You might say, okay, this doesn't tell us enough. It doesn't help us differentiate good from bad type of things. And that's kind of what the final bullet is. We really wanted to calibrate we need to calibrate the thresholds better to use and figure out further study. And then I guess I'm sorry, I just switched it. So one of the things that we did in some further work is we started looking at what happens if you wanted to have a detection window that's not always a lag of 24 hours at most. So that's some of the work that we've started to do. It's just we haven't really finished it or published it yet, so that's why. But that's where we found these results interesting enough that we kind of started pursuing some further results with them. So this is just kind of a recap, so summary of some of the things that we found as we took from lessons learned. I think we had some data that showed these as reasonable assumptions or kind of conclusions to come to. One, the threat-based activity pattern. We found them to be really noisy in our network. In our network, MITRE as a corporation has probably we have 7,000 employees. We have a number of servers so it's not a huge network. It's not 100,000 people. It's not, and so the challenge is if it's really unstable for us there, I think you'd either have to limit the type of clustering to enclaves so you have a lot more stability, or figure out a different way to go. So I think that's the challenge. And that's kind of where I think the network itself, they tend to be enclaved. You get a lot of people behind DHCP, or you get people natted depending on the network. It just becomes, you have to have a really good sense of what the network architecture is if you want to try and do this to some extent. PGP, the PGM stuff isn't necessarily as challenged with that because some of it is just they're going to network resources. So, but anyway, I think network detection needs to be coupled with other things. So. And then, yeah, so that's the challenge for us. Some of this is we went into it saying, okay, PGM is not threat based, but we do have a threat model of how the APT acts. So I think there's useful discussion in figuring out what happens with how do those APT actions translate into PGM perturbations. So when we say they're doing recon activity on your network, what would that look like in a PGM change? So then you could potentially try and merge them, and you say, okay, the metrics, if you see metrics of this that are over the thresholds for these specific metrics, that might lend you to say, okay, an APT is acting within these kind of ways. That's some potential that we looked at. Some kind of standard challenges I think people will find is the realistic available test data for intrusion detection is really challenging to find. It tends to be pretty hard. I mean, we were working on internal data and we had some synthetic data. Finding real examples of intrusion that people will share and allow you to do experimentation with, or creating a network where they come in and adversaries do things is hard. It's hard to just get that data and get people to share it with you. And the visibility from the network is a bit limiting. So that's why a lot of it, I think it's a challenge if you go into it saying, I want to do it solely from the network, at least operationally. And again, that's kind of the skew that I have when I look at these things is, okay, it's interesting research, that's nice, but is it something that if we go to an operational SOC or something like that and say, let's try this, is it something that's going to be even viable for them? And then given the increases of bandwidth and expectations of network services, I don't know that there's any reason to think the variability would change in the near future. So, I guess some path forwards that I think would be useful, like I said, integrating some host and network data. A lot of places, a lot of enterprises are deploying host sensors, so they'll have some notion of what actually is generated from a host, either for data loss prevention or for other activity sensors using the host as sensors. So that then you can start combining and say, okay, I know this host generated these packets. I saw these packets here, and other things like that. You can start getting a more holistic picture of what's going on in your enterprise. It does require some synthesis and analysis. So there's a challenge there. And then red teaming exercises tend to be pretty fruitful if you have that availability and people with that expertise. So I guess that's what I had. Does anyone have any questions? I'm happy to chat or talk. Want to know about MITRE? Go ahead.
Can you talk a little bit about using the Poisson distribution there? It seems like the area under the curve, those numbers for the normal were actually higher.
In certain cases they were, right? So when the T was really high, the area under the curve was higher. And again, I have to go back and exactly understand. So if I'm looking at the December 22nd experiment on the bottom, we're seeing some slightly higher area under the curves for when we have lower thresholds, and then as you increase it, yeah. I mean, I forget exactly what the math was that drove that. That was something that Carrie and I worked on, and it kind of again, this is stuff we did about a year ago, so it might be just me not remember exactly the logic behind it. Yeah, go ahead.
So before with the naive Bayes stuff,
yes.
What was your false positive rates like there?
So
did you apply those to real data?
Yeah, let me go back to that slide so people. So this was some previous work that we've done. I'm not sure what the false positive rates were when he had the red teaming. I know he was able to detect his true positive rate, which was the one that would kind of got him the cachet to get published and stuff, was pretty high. But the paper is available, so I'm pretty sure you can probably find the paper. It's in 2008 rate, and if you want, I'm happy to send it to folks. I don't remember what the exact number is, but it's a constant problem. Go ahead.
In that same line, using maybe a more complex model, would that have helped? Like, using naive Bayes versus some more complex Bayesian network model. Is that something that you guys maybe could have considered, or basically because of the very low true positive rate that you got, you said, no, maybe
No,
that's
yeah,
not
no,
even worth it?
I mean, I came to security via an interest in data mining, so I would, of course, say yes, more complex would be better. But the idea, I think, of that really is the whole assumption of the naive Bayes is that you have, independent detectors, and some of the behaviors were probably not independent. So understanding the correlation of them would maybe lend itself to a better Bayesian belief. Could potentially just a standard Bayes instead of a naive Bayes. I don't know that we've ever published any work that we did in that area, but I think it's definitely one that's open. The challenge I think you get with a lot of these things, if you don't have analysis to get you true positives and false positives, the idea of building or having a learning network or constructing the Bayes is really just a matter of subject matter expertise at that point, right? So then it's a matter of, oh, well, we think these are dependent, or you kind of go back to look at the detectors and say, yeah, these are probably the similar behavior. The ground truthing of getting when okay, yes, this was malicious, this wasn't. That's pretty critical, I think, to being able to do complex structures, because you want to be able to have the labeled data to push back into the structure. If that makes, yeah. And that's a constant challenge with these sorts of things, is having enough labeled data to be able to do. Okay. Well, we've got 10 more minutes, so I can just sit here. Anyone have questions? Or yeah, go ahead.
So when trying to learn what's considered good data and what's considered malicious data, is that going to take you, based on your size of your network, a couple months to 6 months to a year or something like that, just to get a good database to figure out what's considered good on your network? Or how would you go about considering?
Well, so for PGM, we use a 7-day window, right? Or 7 observation model. We said, okay, when we've seen you act 7 days, we have a model of your behavior. So that by your notion, that would be for 7 observations for a user. We said, okay, that's when we have a sense of what you do. Now, whether 7's a good or bad number, we're not sure, right? So we just drew a line in the sand. We said it's 5 business. It's a week and a couple of days. We probably have a sense of where you're going to be going. That's kind of. That's honestly. It was just you have to start somewhere. We picked 7. Now, we did look at some data from other things. If you had less than 7, the models tended to be very erratic, in the sense that people would be flagged as anomalous a lot. As we looked at 7 days, that's when it seemed to be they stabilized a good bit. So, but for your network as a whole, I think that's a fundamentally different question, is what's good. And that ends up not necessarily always being a security problem, right? It might be just a network management problem. If someone screws up a router and it starts jabbering on your network way too much or something, that can cause problems just as much as an adversary. So to some extent, knowing when you've got a good picture of what is normal is a challenge. So, but yeah. Okay. All right. Well, I don't know if I'm happy to be done, but do you guys have any other? Anyone interested in hearing about MITRE? Or so we are hiring, of course. So that's part of the reason I'm here. And we do work in cyber research. That's the area I work in. So if folks are interested, feel free to just. I have business cards, and I'm happy to chat. And we are interested in looking for active research opportunities to collaborate with Purdue. So feel free to ping me if there's anything. My main areas of interest are in this sort of work, detection work, and also in insider threat. I do a fair amount of work in insider threat, so those are my 2 big focus areas. We have a much broader focus within the corporation, but that's the work I do. I tend to work on. So okay, I guess we're done. All right. Thanks, everybody.